Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, good morning, good afternoon, or good evening to everyone's watching. We are from class K31 with our group members consist of Rachel, Yafie, Hanna, Syakira, Azzahra, Alisha, and Sasha. In this video, we are going to explain about our calculation and results of natural fiber measurement using diffraction method to complete our research-based learning assignment. The things we are going to explain are as follows. First is the experimental aim, and then there's the brief theory about the diffraction, and then there's method, data processing, calculation, analysis, and conclusion. So, first of all, the purpose. The goal of our experiment is to use the diffraction method to measure the diameter of a natural fiber that we choose. The next step is to set up the diffraction testing equipment and determine the diameter of various natural fibers based on the diffraction patterns displayed on the tool screen.
Diffraction is defined as the interference of the bending of waves around an obstacle or through the edge of an opening. This happens because the light has the capability to bend around corners. Single-slit diffraction produces an alternating dark and bright pattern. The diffraction pattern is shown in picture 1, where the intensity decreases quickly on either side and the center maximum is larger than those on either side. A diffraction grating, on the other hand, produces lines that are evenly spaced and gradually darken on either side of the center. Next slide. The experimental tool was built with joining 3 boxes with total length is 160 centimeter. A laser holder and a screen made out of styrofoam were glued at the ends of the box, while the slit opening was made of a cardboard with 2 centimeter width of the opening. The slit opening was mounted on a styrofoam in order to stand steadily. Besides varying kinds of natural fibers, the experiment's design also included several variables in order to maximize the result. The determined independent variables are the diameters of a mechanical pencil, the wavelength of the laser beam, and the distance between the slit to the screen. Moreover, the distance from the center of the diffraction pattern to the first dark band is said to be the dependent variable. Next slide. So the Babinet principle states that the diffraction pattern of a narrow aperture is identical to that of a narrow screen with the same aperture width. As a result, the same equations that apply to a narrow aperture can be used to calculate the diffraction pattern of a hair. The same diffraction pattern is produced when a light beam traveling through a narrow slit with width d is replaced by its complement, which has the same width, which is d. This concept is used to measure very small objects. The following equation can be used to calculate the diameter of the fiber using the wavelength lambda of the laser, which is set at 650 nanometer. Next slide, please.
Part 3, the method. So for the materials that we use in this project are cardboard, styrofoam, millimeter block paper, black tape, and the most important, red laser beam. So how do we make the prototype? First of all, we build a base out of cardboards that have been cut into a few pieces and stick it with black tape. And using styrofoams, we make a placeholder for the laser beam by making a hole in the middle of it. We use 2 styrofoams for the laser holder. And for the holder for the fiber, we use cardboard that have been cut in the middle so the laser can go through. And we use washi tape to stick the fiber to the cardboard. And to change the distance between the laser and the fiber, we built a T-shape out of styrofoam and we place it in the base. And last but not least, for this screen board, we use a styrofoam that has been covered by millimeter block paper, so we can count the so we can measure the length easily. And how do we measure the diffraction pattern? First, we place a ruler on the board and we measure the length between the 2 dark points from the point nearest to the brightest point. Next slide, please. And here are the documentation or the photo of the prototype. So in the left side, you can see the base that has been made from the cardboard, and in the middle is the final design of the base, and the right top one is the placeholder for the fiber, and in the bottom right one is the detailed photo of the laser holder. Next slide, please. Part for data processing. Next slide, please. Here are the results of the diffraction pattern. The left one is the result of the mechanical pencil, and the middle one is the result of the hair, and the right side is the result of the leaves.
We use leaf, dandelion, and hair for our experiment, and also a 0.5 mechanical pencil lead as a reference. As we can see from this table, the further the distance L, which is the distance between the slit to the screen, then the smaller the distance X also, which is the distance between the dark bands. Next slide, please. Yes, so as we can see here, there are some trials and errors in this experiment, since the diameter that we obtain from the mechanical pencil lead is not the same as its actual diameter. Next slide, please. Yes, so this is the result of the same experiment of leaf and dandelion, but using a microscope in LF.
Okay, so this one is the experiment of the hair's diameter using LFT microscope, with the result of the average diameter being 0.110 millimeters. Next slide, please. There are several relationships relating the distance between the distance from the fiber to the projection screen L and the distance from the center of the diffraction pattern to the first dark band X, which then resulted in the value of the fiber's diameter. Observed from the experiment that has done, the further the L, then the longer the X is. This also can be seen from the equation 1, where X and L is directly proportional. This could be also seen by the R squared value of nearly 1, which means the equation is linear. And this one is the regression for the dandelion diameters. Next slide, please. And this one is the regression of the leaf, which has the value of R squared, also 1, which is linear.
So this is the regression of the hair. The from the diameter is 0.8, and the regression is 1, which is shows that this is linear. Next, please. And this is the mechanical pencil lead. The diameter is 0.797, and the R squared is 1, which is also shows that this is linear from the distance. The calculating the error percentage, there are significant errors and flaws that occurred in this experiment, such that when collecting the data, the laser and the fiber is not as steady as it should be. Also, the measurement of the distance from the center of the diffraction pattern to the first dark band is not that accurate, since it was hard to measure when the lights were out and the pattern did not appear steadily. Next.
Next one is the analysis. Babinet's principle states that the diffraction pattern created by an opaque body is similar to that produced by a hole of the same size and form. The sum of the radiation pattern caused by B and Bxn must be equal to the radiation pattern of the unobstructed beam. A slit creates a diffraction pattern consisting of a central maximum, a string of minor maximums, and a sequence of minimum points. The diffraction theory is used to determine the minimum intensity of a spot on a screen. Relationships between the distance from the fiber to the projection screen L and the center of diffraction pattern to the first dark band X are observed. However, the system has several flaws, such as the experiment itself and the measurement of the distance from X from center of the diffraction pattern to the first dark band. Next. And to conclude, the experiment's initial goal was attained using Babinet's principal technique, which resulted in mathematical formulae and experiments to calculate the diameter of natural fibers. This experiment also looked at the relationships between the distance from the center of the diffraction pattern to the first black band and the distance from the fiber to the projection screen as a function of diameter. According to the experimental data, S and the distance from the fiber to the projection screen increases. So does the distance of the center of the diffraction pattern to the first dark band, and this can be analyzed and calculated using the obtained equation, where X is proportional to L. Next.
Before we end the presentation, our experiment video will be played.
Thank you, guys.
Thank you.
Thank you.
Thank you.